All right, so we are going to start. Thanks, Louis. I hand over to you.
Hello, I'm Lou. My talk is about optimizing a AAA Vulkan title on desktop. And I'm a dev tech engineer at AMD, so my job is basically to support the game developers that their game runs as optimal as possible on our hardware. So, and I'm also ensuring that our driver does what it's supposed to do. So it's one side fixing the website, but also fixing the server side, kind of being in the middle. And as part of this job, I worked during the last couple of months on a Vulkan title. And this is what my talk is about, just to tell you a bit about my experiences I've done, what kind of optimization did work very well for this title, and maybe just a bit of what we've learned from this process and what maybe we can apply for this game. So unfortunately, I'm not allowed to tell you what title this was. So you kind of just have to believe me. But what I can tell you is that's the first Vulkan game title running with this engine. There was a DirectX 11 version of this engine. There was also an interface of DirectX 12. And then the game developers ported the engine to support Vulkan. And once the Vulkan version was somewhat stable, we started to look in optimizing the game. And that's what the talk will be about the optimizing part. So when optimizing a game, usually you can do like two things kind of in parallel. One is like following the best practices. Hopefully these just require minor changes in the engine. It's not always the case, but more or less. And then also other optimization opportunities, which usually require a bit of more engine restructuring and a bit more work. And you should start this early enough because it takes really quite a lot of time. You can also break some things and you get like new problems. So these both things have to go kind of hand in hand. So best practices, what are these? This is not complete at all, but this is kind of based off what kind of was important for this particular game. So one thing is compression enabled, especially for the cheaper render targets. Then how about the barriers? Are they kind of like in the same state? Can we make use of the copy queue? How about shader building infrastructure? And then like the usual stuff like do we have like the correct usage flags, for layouts, and so on. And yes, this is kind of a checklist. As I said, it's not complete, but you can follow this through for your own game, for example. And then about other optimization opportunities. This is obviously very engine specific. For this engine and for this game, there was a great async compute opportunity. So what it basically is about is that if you have two frames, so frame 1 and frame 2, you could overlap the beginning of the frame with the end of the frame with the beginning of the next frame. So basically do something like this. So if this is the post process, then you can overlap it with the pre-process of the next frame, but then still present on the graphics queue. And what's Vulkan specific, you can also present on compute queue. You can do this. But if you do this, I recommend that you still have this path as a fallback in your engine just because of tooling, because not many games do this kind of stuff, so it can break tooling, but you definitely can do this. So, and you see it's kind of like, yeah, you have to switch back and stuff, and you not just this would be. Yeah, so what I'm going to talk about in detail during this talk is compression. And to be more precise about DCC, data color compression is the technique we use in our hardware. Other vendors have their own compression techniques, but in this talk I will obviously just cover DCC. Then about barriers, what we did for this engine and for this game to optimize them, a bit about other synchronization problems and more smart things. So, but let's start with DCC. And this is like the checklist I mentioned before. And also won't forget async compute. So this will be also pop up during the talk. So yeah, but let's start with DCC. So DCC is data color compression. I will talk about a bit what it exactly is. Then why do we want it? Why should we care about it? What's the performance impact for this particular game? And how do we enable DCC? So this is like the most interesting question. So but what is DCC? So DCC stands for data color compression. It's for color targets. That's why color compression, and it takes advantage of the fact that render targets usually have slow varying data. So if you look at a blue sky, while most of it's blue, and there's like little variance between them. Another example is if you look at this picture, it's mostly beige. Kind of fascinating. Even the floor of the raccoon is also kind of in the color of its surroundings. So you see it's like little variance between the neighboring pixels, and DC basically takes advantage of this. So on a very high level detail, what it does, it stores whole blocks, and one value is stored in pole position, and all the other values are stored in deltas, like as delta. And not one thing, it's lossless. So if you enable DCC, you don't lose any of the image quality. Yeah, so kind of like I want to enable it. And why? Because it saves bandwidth, basically. So if you do a lot of writing and reading, you save it. And like experience showed, it's very beneficial for cheaper render targets. It can be also beneficial for other resources, obviously, but if you have to pick a few one, then I would recommend you first look at the cheaper render targets, because just experience showed that they usually benefit a lot from these bandwidth savings. So how much? Well, for this game title, you observed speed-ups on all tested AMD cards, ranging between 5 to 10%. But of course, it really varies. It depends on the workload. It also depends between the graphics card, but for this game title, it was quite beneficial, so it was really a nice game to get DCC enabled. So this should be quite convincing, right? So let's talk about how we get DCC enabled. And unfortunately, there's not just like a setting you can set, oh, DCC enabled, because the driver will enable it automatically if it's safe to do so. So as developers, we have to kind of ensure that it's safe to do so, and it depends on a number of different factors. So the first step is that you should just check if DCC is maybe already enabled, because if it's already enabled, you don't have to do anything anymore, right? And to check this, you can use RGP. It's the image group profiler. Take a capture, then you go to the overview tab and the sub tab render dev targets. There you will see a list of all the render and dev targets in your game. And there's also a column that says compression, and there you can check if it's on and off. And for this case, these are the cheaper render targets for this game. And when I checked, it was off. So this was quite sad. And the question is, why is it off? And how can we figure out this? So the first step is you can just stay in this view using RGP and have a look at the formats. DCC is possible for float and integer formats. I can't give you a complete list, this would be like too much here, but in general, all the common formats are supported. So for this case, like RGB, A8 sRGB, or UNOM, those are supported, so the formats here are not a problem. Okay, so format's not a problem, what to do next? You should have a closer look in the resource. To do this, you can take either use render node, and go to resource inspector and then just click on the resource in question, or obviously you can also just look in your source code. So in Render, you see the create info structure from the image, and then you can check the format. As I just said, it's fine in this case. Also the usage flags are fine. So in this case, it's the transfer usage bits, the sample bit, and the color attachment bits all work with DCC. So these are not a problem. Sharing mode is sharing mode exclusive. This is also fine. What's not that fine is the image create mutable format bit. Why? Because it disables DCC. Why does it disable DCC? Well, when I talked about format support, I wasn't very precise because DCC only works for float, exclusive, or integer formats. So if you only have one format, that's kind of given, right? If I have a float format, DCC supported. If I have an integer format, DCC supported. And how does the driver know the format of the image? Well, it just looks at the image create infrastructure. There you provide the format, and everything is fine. But what happens now if you have the mutable bit set? Well, let's look at the spec of the mutable bit. It says that we can have an image view with a different format. So this basically makes it impossible for the driver to rely on the format information from the create infrastructure. But this is important because the driver kind of needs to distinguish between those formats. The driver needs to know if it's an integer and float format used, because in this case DCC has to be disabled. If there's maybe a format used which is not supported by DCC at all, then it has to be disabled as well. Or if you only use float formats, then this is enabled, can be enabled, or if you only use integer formats, this is the same. And by simply looking at the module bit, the driver has no idea which of the following cases we have. So we kind of need to provide the driver with additional information to make the smartest decision here. Because if you just have the module bit, the driver has to play safe and just disable DCC. Even though in theory it would be possible, but the driver just has to be safe in this case. So how can we provide the driver with more information? Well, luckily there's this extension, is the ph.image format list, and here we can give the driver a list of all the image formats which have to be supported by the image, and based on this list, the driver can make a smarter decision. So how can we use this list? Well, we just provide the number of formats and then the list of formats, and the structure is passed to the next pointer from the image create infrastructure, and then the driver can make, based on this list, the best decision. And the game dev did this. So in this case, for the G-buffer targets, we have two formats. One is UNOM, and the other one is actually this RGB, and both are integer formats. So this is fine for DCC, and DCC can be enabled. But let's check in RGB if DCC really got enabled. And when I did this, sadly it was still off. So I was kind of, okay, what's the problem now? So let's go back to another and check what was wrong. And well, format is fine, format's fine, user specs also fine, but the sharing mode changed from exclusive to concurrent. Why did it suddenly change? Well, during the weeks when the developers added this, they also added async compute support actually. And as a side effect, now all resources had as default the sharing mode concurrent. And it's, yeah, this was kind of like, whoop, because sharing mode concurrent actually disables DCC. And what does sharing mode concurrent do? Well, it makes it possible to access the resource from different queue families. And this is just a property which is not supported by our hardware, so it would be quite difficult to enable DCC, so it's just disabled basically. And yeah. So now on all our resources in the game, DCC was disabled as a side effect to async compute support. Another note for async compute support on this, they actually did what I mentioned in the beginning of the talk. So they overlapped the post-processing step from the frame with the pre-processing step of the next frame. And this change actually gave a speed up of about 10%, also depending on graphics card, of course, but overall it was quite a success, I would say, to add this async compute support. So in general, it was a good thing. But because of this, we still had no idea about the effect of DCC on the G-buffer render targets, because at this point, it was always disabled DCC. So, but let's keep trying and try to get DCC on, right? So for this, we had to kind of switch back to exclusive. And if you have resource which is only accessed by one queue family, you can just safely switch back because concurrent is just not needed. But interesting are the resources which are actually accessed by several queues, so which are accessed by the graphics queue family and by the compute queue family. Because in this case, we have to do transfer the queue family ownership. And how to do this? Well, it's done in two steps. First, you have to release the ownership from the source queue family, and then after it's released, you have to acquire it from the destination queue family. And this releasing and acquiring is done via barriers. So let's just step through a small example. So an example, queue family 0 holds the current ownership of image A, and queue family 1 wants to acquire it. So first, queue family 0 has to release it. So it has to issue a barrier, and source queue family has to be set to 0, and the destination queue family has to be set to 1. This barrier has to be issued in a command buffer which is associated to command pool, which is associated to queue family 0, basically, and then you have to submit it. And here with the submission, we have to also use a similar to sync across the queues, just to be sure that the releasing really happens before the acquiring. And then the acquiring happens on the destination queue family, and in our example, and so on. And once we've done this and have like handled this queue family ownership correctly, we can safely switch back to sharing mode exclusive. And once the robust did this, I checked RGP again, and luckily, finally, VCC was enabled, and this was quite more. And then you also could check for the performance difference. And yes, I mentioned this already in the beginning of the VCC chapter. You could see between 5 to 10%, depending on AMD graphics card. So this was another quite nice performance setup. One last thing you may have noticed, one chipper was still VCC off. So why? Let's check again render doc, and yes, format is still fine. Share mode exclusive, you can see it here. It's changed now back from concurrent, but now we have here the storage bit for this specific cheaper render target. So it's just resource number 2. I call it here. And why did I add a storage bit? But it's also related to the async compute change, because they moved all the post-processing from the graphics queue to the compute queue. So what was before a full screen fragment shader pass and was now a compute shader pass. And this made it required that this resource number 2 from gbuffer had to have now the storage bit. Why? Well, the storage bit specifies that the resource can be used as a descriptor type storage image, which supports load, store, and atomic operations. And important is here the store, because before we had a fragment shader, and then in this fragment shader, the gbuffer resource number 2 was just used as a color attachment. And when it was changed to compute shader, it was now a storage image, and the storage image had to support store operation. So we now needed this storage image bit. This is totally fine in this example because we needed this bit, but as a side effect, VCC was disabled because it's not the storage bit is VCC. It's just a great reminder that you should always use the user splash bit you really need. As I said, in this example, it was totally fine because we needed it. But if you would have set it by default for all gbuffer resources, for example, then we still would have like VCC disabled on all gbuffer resources. Another sample usage flag which influences DSC is the sample bit. It makes DSC less efficient because if the resource is only written to but never read, we can make some additional optimizations in the compression technique. But if you have the sample bit, we have to assume that we also read at some point the resource, so compression will be less efficient. Yeah, so just keep in mind, always use what you need, but not more. To wrap this up about DCC, I'm sure that it gets enabled. If you use the great mutable format bit, it's totally fine, but I always recommend to also use the image format list. And sharing mode exclusive. You can use sharing mode concurrent for like first versions of async compute, that's totally fine. It makes it easier to not deal with the additional burden of several queue families and stuff, but I don't recommend it to use it in production ready code. For that, I recommend still use sharing mode exclusive and just transfer the queue family ownership. It's usually more performant than having the concurrent sharing mode. And user flag, yes, set all the user flag you need, but no. Then other smaller nitpicks concerning DCC. DCC is not only about enablement, it's also about decompression. Sometimes decompression happens. For example, during transfer operations, you can have a decompress. Also, if you set the general layout, and this is, for example, if you have a case where you only read the resource, but you don't set the shader read only bit, but shader read only layer, but the general layout, then you have a decompression, and that's actually what here happened. The resource was just read, but they still set the general layout, and then you have a decompression which took up a certain amount of time of this whole pass, even though it wasn't needed. And then def targets gets also compressed, but not DCC compressed. It's a different compression technique. It has different rules, and everything I told you about does not apply to def targets, even though it's in the same column in RGP. I just meant that you don't get confused, because, for example, if you have for all the resources sharing mode concurrent, we still see that dev targets are compressed and just don't get confused by this. And then just kind of like a warning, because there's no rule without exception, right? Sometimes there are tweaks in the driver for special cards. So something can happen, you follow all the guidelines and then C could be still disabled or something different happens. Just don't be confused by this. In general, you will be fine because it's really just exceptions, but just be aware of it that sometimes you may observe different behavior than expected. Yeah, but it's all about DCC. Now let's go to synchronization, and in particular about barriers. It's about placing them as smartly as possible, batching consecutive barriers, and also a bit about pipeline stage mask. We heard about this in the beginning, like the first talk, talked a lot about this. I will just talk really briefly about it, and then also synchronization. So barriers. Most of the stuff I talk today is basically just the experience I've made with this engine, and the issues we had with the barriers most likely had their roots in the original engine structure, which is DirectX 11 based, and DirectX 11 does not have barriers. And then how we solved this issue was just by rearranging barriers, batching them, and then some other findings, which is related to the pipeline stage mask. So, but how did the original engine setup work? Well, the original work was logically organized in components. Let's say there was like shadow map component, lighting component, dynamic models component, and so on. And each component had constants. So in these constants, the information was got already in the beginning of the frame. So when we started to like record all these commands, and we already knew the constants associated with the components. And then let's go through an example that you understand like how it worked in the engine. So you have the constant information already in the beginning of the frame. Then constants A, B, and C are actually equal, and constants D is in this example different. So most of the constants they didn't vary between the components, just a few were different. And here in this example, A and B is independent, C depends on A and B, and component B depends on component C. And if you lay out the frame graph, how they rendered it, what they did was that they updated the constants right before the associated component. So what we have a barrier to make the correct layout transition for the constants buffer. Then the update happened. Then we had another barrier to ensure that the update was done. Then we had the component, all the store commands, and then we had the next update constant for component B, and so on. So you see the work was very sequential. Even though between A and B is actually not a dependency, but because of this updating the constants, we had like this artificial separation between these components. So how can we make this better? Well, the first step is just rearrange. So just place all the constants in the beginning of the frame because we already have the information. So just do first update constants A, B, C, D, and then after this, do all this other work. And in this case, these will overlap because now we don't have a barrier between them anymore. And then we can do some further optimizations is by actually batching these barriers and let the update constants overlap because they also don't depend on each other. And because these three are actually equal, we don't have to create redundant copies. We can just update it once and just let the components refer to the same location, so we reduce the number of updates. What we ended up with in the engine was actually just this step. So we just rearranged it just because of time constraints. We also have like the updating just sequential and then all the store commands, but this already showed the significant speed up. So what we had before, this was these are the G buffers. So you see there's a lot of holes because of these updating the constants. And when we rearranged them, we got rid of the holes basically, and we also got a bit more overlap between other render targets, but also in between the cores. And you see it in this view better. So you see the occupancy got higher just because we have more overlap. There's more work for the GPU to process, and we didn't train the GPU because of these barriers for the constant updates. And for the G buffer parts, we could observe the speed of about 15%, 10-15% depending on the scene. And this was quite nice, just by rearranging the barriers and placing them in the front of the yeah. Another thing we did for barriers using was batching consecutive barriers. So in early builds, we had like 10 or even more barriers right behind each other. And this is not necessary. You can just issue one pipeline barrier, including all the layout transfers. And you can do this because in common pipeline barrier, you can like specify the number of all these barriers and then just define the list. So if you have an example, for example, you have 2 image layer transfers, the naive way is just for each image layer transition, you can issue a separate common pipeline barrier. Or what's the better way is you just create a list of all your image layers and then submit it in one row with one pipeline barrier. And this also saves a bit of time because you don't have the overhead of committing all the separate common pipeline barriers. Yeah, pipeline stage mask. We heard about it already in the beginning of today. So it's just if you have like dependencies here, you don't need to wait until the bottom and overlap them. What I want to talk in specific is the all commands bit. So the all commands bit is equivalent to the logical OR of every other pipeline stage back supported on the queue. And I want to specifically talk about the all commands bit on the compute pipeline. Because here from the compute pipeline, it includes the transfer stage bit, the compute shader stage bit, and also the bottom stage bit. And the bottom stage bit should not be ignored because it adds actually an end of pipe timestamp. And this can take up to 64K cycles on the async queue. So I recommend not using all commands bit, just use the specific pipeline stage mask you really need. So for example, use state compute shader bit or stage transfer bit. And you will save a considerable amount of time. So for example, first we had the all commands bit. So it took like 0.044, it's like synchronization is full. And then when we change this to compute shader and transfer bit, it's way less. So in this like small change made like huge improvement for the async compute clusters because before we had a lot of idle time just for these barriers. With this change, yeah, we got rid of them. Yeah, this right. This was all about barriers. Now a bit about host queues on synchronization. Before we had async compute, we didn't have to deal with it. So the engine just had about 7 command buffers per frame. When async compute support was added, the amount doubled. And this was due because of synchronization, because at each sync point, we actually had to like submit the command buffer and issue a new one. So you can see the change here. Now we have all this semaphores and stuff. And it's not optimal how they handled it. They also submitted sometimes empty command buffers just for the sake of synchronization. There would have been a way to get around this, but it was just not feasible in the time frame because it was async was added, then it had all to like deal with the other stuff, and then also deal with empty command buffers was just too much, and so short for release. But that's how they ended up with, just like not optimal, but it was okay, and it's just like a kind of observation we've done during the process. That cross-queue synchronization was like, yeah, okay, we had like some like ugly command buffers and empty stuff to deal with, and here like a lot of small command buffers as well, but it's just, yeah, a side effect. Yeah, quick summary. Check the barriers. Can we rearrange them? Do we really need to submit the barrier right before we need it, or can we maybe move them to an earlier stage? You can batch them if they're consecutive. Specify the stage mask as precise as possible. You can really save a considerable amount of time. And yeah, cross-queue synchronization is only process submission queue boundaries. Yeah, and then now just other small things. It's really just more, I won't talk too much about it. It's about the copy queue, a little bit about the compute chain and compute to and swap chain. I talked about in the beginning, and then a bit about shader building. So the copy queue. Copy queue is if you want to yeah, copy basically from the GPU to CPU. If you want to do GPU copies, I wouldn't recommend it. So it's basically if you want to do copies which are not time critical. And for this game, there was such a case. So there was a resource, we just needed to copy from the GPU to the CPU. It was not time critical, like the resource wasn't needed in the first half of the frame at all, so we had like plenty of time to do it. And before they just did it on the graphics queue and was like blocking the whole GPU for about 1 or 2% frame time. And then we switched it to the copy queue. Here you can see this, and basically saved this 1 or 2% back. And it was the sync point. It wasn't completely free because we had to sync, but it was still way less time than we spent for doing this copy on the GPU. Of course, doing this copy, nothing else could be done doing on the GPU. Yeah, then about compute queue and SWAPCHAIN. I talked about it in the beginning already. On Vulkan, you can directly draw from the compute queue to the SWAPCHAIN. Here they didn't do it actually on the engine because it needed to be like also work on other versions, so not only on Vulkan PC but also on consoles and stuff. So that's why they had like this copy. So basically they used the intermediate texture for the compute shaders, and then they copied this result to the SWAPCHAIN on the graphics queue. And this is basically, this is the whole UI, and you see this copy is taking about 1/3 of the UI computation. So in Vulkan actually does not need it, so you could just skip this and just draw and render directly to the compute. And yeah, you could basically also present from the compute queue, but as I said, I would always have this path as a fallback as well, just because of tooling. And this is the last topic. It's about the shader building infrastructure. So in this game, they used HLSL shader code, and they had all those shaders already in HLSL. It would be like not feasible at all to rewrite them in HLSL, and I wouldn't recommend it either. And in the beginning, they had the TLS-Lang validator, but then they switched to the DirectX compiler, and it's also what we basically would recommend, because this path, like SphereV generated using this path, is the code our shader compiler sees the most. It's the most common path, and this also means it's the most optimized path. So SphereV generated by the DirectX compiler from the HLSL is the most optimized version. Yeah. So that's basically it, just as a reminder, check for compression, especially for cheaper for render targets. If you have to pick certain resources, then have us look at your barriers. These are really important for performance. Is there a possibility to use the copy queue? Yeah, on Vulkan you can directly render to the SWAPCHAIN from the compute queue. And please use the DirectX compiler and write your shares. And yeah, thanks to these amazing people, it's obviously possible. Also, thanks a lot to the game devs. Unfortunately, I can't mention them, but thanks to them a lot. And if you want to read additional information, you can look up. And yeah, now if you have any questions, please ask now or write me an email, send me a DirectX message, or ask me later.
I have a question about, is it possible to add an extension where you could say, here's an image create info, will this have DCC?
I think in principle it's possible, it's just, I'm not sure if we want this, but probably not, because we don't really like using, shipping a lot of extensions, and most of them will never get used. But could be something.
If there was demand for it, we'd do it.
Yeah, but right now I don't see it, yeah.
Yeah, because I've seen cases on this is like very Polaris specific, but I've used concurrent where I render an image and I use it shader read only in the compute queue right afterwards, but I seem to get DCC anyways.
Yeah.
So that's a bit confusing. Are there some rules where concurrent can still have DCC in the driver?
I think concurrent mostly breaks if you concurrent with the transfer queue. I think there are cases where you need concurrent on the compute queue that it will still be active. I'm not sure what those are.
Yeah, I think if you have the concurrent mode, by default it's just disabled, because basically the driver doesn't really know how will you use the resource, even though it would be possible in theory.
Yeah, yeah. To clarify, because when you have concurrent, you can specify exactly which families it's concurrent with, and then I also use only graphics and compute, not transfer.
Yeah, the main issue for us is that if you are concurrent with the transfer queue, it can't do decompression. So you kind of have to stay decompressed at all times in order to be able to use that queue. I think that compute queues can handle most decompression, not all of them. So there are cases you can do. You can stay compressed in cases where you can't. I haven't tried to see exactly what they are.
In DCC, you said that one of the components is full precision and the others are less precision. Which component is full precision?
You mean how it's stored? Usually it's the block, and then one pixel is like stored in full position, and the rest is just stored as delta.
Right. Okay, and that will be in the RGB space.
Actually not sure.
So that was going to the YUV or something.
No.
Yeah, but basically you don't lose any information.
Okay.
So the image quality or anything is not affected by this.
Do you have any numbers on the compression ratio in best and worst case scenario?
Not really. It highly depends.
I think we have some information publicly about DCC that has this, but I don't know what it is.
Yeah, I don't know.
So about the async compute and presenting for the compute queue, I think that's an extremely nice optimization, and I'm a bit surprised to say that to hear that you say that we should do it because of tooling.
Yeah, I mean, not many games present on the compute queue right now, so it's not really proven that it works in all cases. I mean, I think it works for Doom. They do that, and tooling works.
It just sounds very terrible to sync back to the graphics queue, and then the graphics queue, it has to like sync to the SWAPCHAIN, right, where you could leave all that on the compute queue.
I think if more games would go this path, then the tools would also be more robust.
Okay.
But in this stage, I would still recommend the other path, just for debugging stuff.
Okay, so it's like RTP and render doc, stuff like that.
Right.
Okay.
Do you also get DCC for uncompressed textures, or this is just render target specific?
What do you mean?
Do you mean when you're uploading a texture? No, I don't think so. It's only sub-generated by rendering, as far as I'm aware. I think it's technically possible, but I don't think we have that.
If I were to access a DCC texture, which do you recommend? Which fragment or compute, or how do you recommend it to access in the best way? Say if I need to do distortion from a render target.
I'm not sure if I understand.
Which?
I mean, like if the texture is compressed, it's basically kind of invisible to you.
Okay. But you said
the shader core can handle compressed data.
Yeah, you said there was some flags that affected the DCC compression.
Yeah. So for example, the sample bits makes it less efficient.
Okay.
But you still can read compressed data. It's just not that efficient anymore. Any more questions? Yeah.
Is there a difference between shader read and input attachment there for DCC performance?
and thanks a lot.
So now we'll arrange the room 5-10 minutes for the panel discussion. So if you want to grab some more food, a tea, quickly, 5-10 minutes, we are going to be back.